Okay, let's get started. Okay, hello everyone, welcome back. So I think we started with a great keynote and a very interesting debate. So now we have our second keynote in which is the first talk of the afternoon, and it is my pleasure to introduce Martha White. Martha White is an associate professor of computing science at the University of Alberta. There's an echo. I have two mics together. At University of Alberta and a fellow of AMY, which is one of the top machine learning centers in the world. She holds a Canada C4A chair, a Tier 2 Canada Research Chair in Reinforcement Learning, and received IEEE's A8's Tend to Watch, the Future of AI Award in 2020. She has authored more than 70 papers in top journals and conferences. She's also an associate editor of JMLR and TMLR and has served as co-program chair for ICLR and RLC, which just happened a few days back. I think she's directly coming from RLC to CoLLAs, and she regularly serves as an area chair for top AI conferences. Her research focus is on developing algorithms that learn to adapt continually, which is exactly the focus of the conference. And she has an extra focus on more sustainable systems as well. So she's going to talk about leveraging traces for continual R. Thank you.
Pleasure to be here. If it's hard to hear me or if I'm talking too fast or at any time, please interrupt me. I know this is a pretty broad group of in terms of topics. So I'm going to be talking about reinforcement learning today. I don't expect everyone here to be a reinforcement learning expert. So as I go along, I'm going to kind of assume everyone doesn't know exactly how to train recurrent neural networks or reinforcement learning or what eligibility traces are. So I will sort of do some of the very basics, but I'll try to go through it relatively quickly and then get to the stuff that's of interest. But I think when it comes to a relatively broad group like this, one of the most important things is to make sure that we all know what problem setting I'm talking about and we're sort of all on the same page. And then we can talk about, are the algorithms I'm proposing actually a good idea for that? We can have a good argument about what I say rather than about what problem setting we're talking about. Okay, so let me tell you what my goals for this talk are then. As Sarath mentioned, I care a lot about continual learning, especially in the reinforcement learning setting. And so I'm going to start off by telling you what is the setting I'm thinking about when I think of continual learning. So I'm going to particularly motivate general purpose agents that learn subtasks in parallel. And so I'll tell you a little bit about, to me, subtasks are actually about learning and options and value functions. And that, again, motivates why I look so much at reinforcement learning algorithms that learn option policies and value functions. And then specifically because of this word parallel, I want my agents to learn many things about the world. That's what it means. It needs to learn many options and value functions in parallel. And so we want to have lightweight algorithms for learning each of these things. So that motivates, again, why want to care a lot about incremental algorithms. So in reinforcement learning, we often have buffer-based algorithms. They're kind of computationally expensive, memory intensive. And so moving towards more incremental algorithms, one of the ways we can do this is to look at traces. Okay, and so I will tell you more what traces means as we go through the talk. So there's a lot of jargon on this slide, but I'm just sort of setting you up for where we're going, and then I am going to work my way through it. So the first part, I'll tell you, in general, for the whole talk, I'm going to tell you about two different ways that my group is looking at using traces as a way to be more incremental, so efficient without having to rely on these big buffers. It's almost like two different talks stapled together, but they really are all about leveraging the beauty of traces. So it felt worthwhile to me to tell you about both of them in this larger talk about these types of algorithms. So the first one will be about using traces for recurrent learning, and there I'll tell you a little bit about a recent work about this new architecture we're calling recurrent trace units, or really just a little unit inside recurrent architectures that leverages RTRL. And RTRL is exactly a trace-based algorithm. And then I'll tell you a little bit about some work in doing more efficient credit assignment and reinforcement learning, which relies on lambda returns. And they're specifically about making these algorithms better by using gradient-based approaches. Okay, so lots to do. I'm going to go through at a reasonably clipping pace. And again, I encourage you to interrupt me at any time and ask questions as we go. I'm kind of naturally an educational presenter, sort of just my style. So I love more when we have some engagement with the audience and you actually feel free to voice thoughts. Okay, so let me tell you about what is my motivation for the types of algorithms that we develop in my lab. And so I care about the online reinforcement learning setting. Just drawing the picture here, you have an agent in some states, going to take actions that impact the world. It's going to transition to some new states and see some reward. And the agent's goal is always to be improving its policy pie. That's the thing that's actually taking actions in the world. towards the goal of getting lots of reward. So here for maximizing my expected return. And so I want my return to be high. I want to have my actions now, not just making sure I have good reward immediately, but good discounted reward into the future. Now, now for this, because maximizing expected return is so critical for our RL agents, that means most of our algorithms are going to be doing some attempt to estimate that value, estimate that expected return. So our algorithms are going to be estimating things like value functions and action value functions. So I told you I started at the beginning, but again, this notation is going to sort of set us up for where we're going. So my value function here, for example, is going to tell me what's the expected return if I were to follow this policy. And particularly, we often will also leverage this ability to bootstrap off of our own estimates. So instead of having to wait to see what all the possible rewards are, if I were to execute a policy, I can ask, this is the immediate reward that I just saw, and then I'm going to use my value in the next state as the best guess for what my return is going to continue from here. So we won't just learn value functions, we're also going to want to actually improve the policy. An action, very beautiful thing is that we can learn action values and then locally be more greedy, and that can actually guarantee that we're going to have a better policy. And I almost feel like sometimes we take this for granted in RL, how nice this local improvement property is, but it is really fundamental to so many of our algorithms that I can say, given that I was in this state and I took this action and then I continue to follow this policy from here, if I were just to locally say which action would have given me slightly higher value, so I'm going to take the argmax, then I'm going to get a better policy. And I can slowly improve my policy through this procedure. Okay, this is my last RL, let's get our basics together and our jargon together slide. So just to give you an example of what one of these algorithms would actually look like, and then sort of motivate why this is not going to be enough. Consider this very basic model-free agent. Q-learning is a broadly used algorithm, or Q-learning and its variants. Q-learning is going to learn some action value Q-hat, usually parameterized as a neural network. We'll define some stochastic policy on those action value estimates, like an epsilon greedy policy that takes random actions with some epsilon probability, or some kind of softmax that adds some stochasticity. But ultimately, Q-learning is trying to learn what's the best thing to do in this state. It's trying to learn a greedy policy. So the interaction in the environment looks like in some state. It's going to sample an action from this slightly stochastic policy. It's going to transition to a state, see a reward, and then it's going to go do this very simple update. So if you notice in this update, we have some estimate of what do I think the return is going to be for having taken this action. And I want to make my estimates closer to the return that I actually saw. So this looks just like a linear regression update. And the only thing that's different here is this return that we use. So the return is exactly using that bootstrapping property of, here's my immediate reward, plus what do I think is going to be the value for the best action, the greedy action, in the next state. Great, so this is a very simple algorithm for this problem. Despite its simplicity, this is still underlies DQN. It underlies a lot of successes out there. So again, pretty cool that these simple algorithms can do these, can address these hard reinforcement learning problems. But in general, we can ask ourselves, how far are we going to get with this very simple learning update where I'm just doing this trial and error interaction? And I think many of you will agree, but I'm going to argue a little bit that we're going to need a lot more for the continual learning setting. So in the continual learning setting, we have many, many steps of interaction, this very long running interaction, and we're going to have potentially vast environments. So I'm just going to be very concrete about it and give you a cutesy example that's going to let me tell you about what other kinds of subtasks that I'm thinking about. So for example, you could imagine a robot. You want your robot to be picking up and dropping off packages across the city. That city is complex already. There's people moving around. Things are always changing in the city, but maybe actually the city is growing. It's just a large, vast, ever-changing environment. You can also have non-mobile systems that still are going to live in very complex environments. For example, an agent that's controlling HVAC for a network of buildings. Again, you're going to be deploying new sensors. You're going to actually be probably building new buildings at different points. People are going to be moving through those buildings. So these are the kinds of problems we would like to have agents actually deployed in. Okay, so let me just go a little more deeply into, well, if we're doing this thought exercise and we want to move beyond this very model-free update, let's think about what would we want the agent to actually know to solve some of these problems, or what I want the agent to know. So I think this RL agent is going to need to make lots of predictions about its world if it wants to do a good job of this. So what will happen if I pick up this object? How many steps until I get to that door? So again, because it's trying to drop and pick up packages, so it needs to be able to answer those kinds of questions. How much longer can I keep driving before I have to go back to some location and recharge? Can I go do one more package drop off, or do I have to go back and recharge now? Okay. So in general, when you're going to have this very long sequence of interaction, the agent should accumulate knowledge about its environment because it can then reuse that accumulated knowledge, but it can also learn and adapt faster in new situations and when the world is non-stationary. So in a lot of the problems we deal with in RL, like if you're going to solve cart pull or something very simple, it's kind of overkill to think about these kinds of solutions. You should just go and find your optimal policy. You're done. There's nothing much more to do. But you sort of have the second order effect where it's worthwhile learning models or options or things like that if you're actually going to be reusing those kinds of things. Okay, and that's exactly what we'll be doing in our continual learning setting. Okay, so the specific pieces of knowledge that I would like to learn, I think is a powerful language is just with two different types of subtask specifications. And so those are both options. Options are skills. Sometimes people interchange those words. They're mostly the same. I'm going to think of those as control subtasks, and the other ones are prediction subtasks, which I think can be well represented in the language of general value functions, which I presume not many of you have heard of, but I'll just give you a brief understanding of what those are. So I'm not going to dwell on this, right? This is mostly just motivation for the setting I'm thinking about. But again, I'll give you just a little bit more of an example. So going back to this robot, you might want to learn a policy, for example. So we're often called these option policies because they're not the larger policy we're trying to learn. It's just going to be a smaller policy within this environment. And so maybe we want to learn this option policy that navigates to the lab. The lab is where I can actually go recharge, for example, or go get fixed or whatever it is that happens there. So this is going to be a smaller little learning subtask. Maybe you can even learn that with Q learning. But still, this agent's goal is not to navigate to the lab. Its larger goal is to maximize reward in the environment. So it's in a continuing environment. It's constantly just trying to get as much reward as possible. But this subtask is going to help it with its primary task. Okay. It's also, this option can be repeatedly used sort of in two ways. Maybe the most obvious way is I could actually just use this as a macro action, like executing this as a skill. I like to think more about using these options actually for planning and reasoning. The agent can reason about, again, should I go to the lab first? Should I go get recharged? Should I go fix this? Or should I go do that? So I can do a bunch of temporally abstract reasoning in its mind with these kinds of subtasks. Okay, and then just some examples of prediction subtasks. So there's this really nice language that's been introduced within the last probably at least 15 years now called general value functions, recognizing that value functions are not just about estimating expected returns for a reward. Actually, you can use this exact same language to ask questions about many different signals into the future. So for example, you could use a value function form. You could answer a question like, what is the probability I will successfully plug in if I run the navigate to lab option policy? Okay, so you can actually specify by specifying a different type of reward called accumulant. You can use the exact same algorithms used to learn value functions. We can use those to learn general value functions, and we can specify all these different types of prediction subtasks. Okay, so I encourage you to go read about general value functions. They're cool, but that's mainly all I want to tell you about my motivation. So I'm imagining agents that are learning a bunch of general value functions, a bunch of options. They could be learning hundreds of these things and probably also constantly adding new ones as they realize or discover that there's new pieces of information about the world they want to answer. Okay, now, so in this problem setting, in this continual learning setting, what algorithms could we actually use? So I would argue actually we could technically do this today. You could go grab existing deep RL algorithms. You could learn option policies and value functions, also off policy with neural networks and in parallel, but it's not going to work very well. So there are going to be some algorithmic issues, and these are the kinds of issues that I want to address. So let me just tell you four at least kind of obvious issues with doing this. So most deep RL methods rely on buffers and replay. And this is actually a very sensible thing to do. If you've been interacting with the world, you store as much data as you can about your interaction. You should keep that information. That's a lot of information about the world. And it's very natural to go do a bunch of updates on that data, little mini batch updates, especially because that lets us leverage all the insights from supervised learning and port that over into the reinforcement learning setting. So in general, buffer-based algorithms are powerful, but in our setting where we need to now learn hundreds of things, there becomes some issues with this. Okay, so the first obvious issue is just a storage issue. If you're learning many, many things, there actually might start becoming a trade-off between, should I have bigger neural networks? If I'm going to have independent networks for all of my subtasks, that's now actually a large number of neural networks. Or even if you cluster some of the tasks into different networks, Now you might actually be trading off capacity of your function approximators for the data that you're storing. And that trade-off may not come up in on some of our single task problems, but it actually probably will here. Updates can be pretty computationally intensive. So it's, again, a straightforward and nice, simple thing to do, just to do a bunch of mini batch updates, but they're not the most computationally effective updates. We can be smarter about how we allocate our updates. And that becomes extra important when you're updating hundreds of things. Non-stationarity is not something we often think about in the regular deep RL setting, but again, obviously comes up in the continual RL setting. And now you have to sort of make these trade-offs between how much do you trust your old data versus not. You have to sort of recognize when that data is out of date. And then the last one is partial observability. So the randomized mini batch updates that we use on our buffers are very well suited to, I have the Markov state property. It's easy to grab just little tuples and to do updates. Once you start moving to recurrent architectures and needing to use histories, of course, there are strategies. People use recurrent algorithms with RL, but there's all these weird, unnatural choices you have to make about how to use buffers and treating recurrent neural networks. So there's some, it's not that it's necessarily an issue, but it's not clear our algorithms are particularly well suited right now to these kind of mini batch updates. Okay, so this motivates some level. Is there something else we could do? Maybe we could start going back to something we had done long ago in RL. It was very common to use, for example, eligibility traces as a way to be efficient in how we update, being sample efficient before we really started using buffer-based strategies. And so let's try to explore a little bit this sample efficient but still incremental updates by leveraging traces. Okay, so the two scenarios I already told you that I'm going to talk about, two things that I think are important. One is handling partial observability, and the other one is efficient credit assignment. These are the two now. I'm going to dive deeply into these two specific topics, but I'm just going to now say thus ends the motivations section of this talk. Now we're going to sort of myopically do what we usually do. We know what our larger goal is. Now we're going to carve this off and just ask, could we come up with good trace-based algorithms? We're just going to do it in the single task setting, simple episodic problems. Everything is stationary, knowing that this is sort of towards this larger goal of the parallel multitask setting. So you're not going to see me run any of these things in this larger continual RL setting. Our goal now is just to understand, can we develop good algorithms, which will then help us move towards there. Okay, so let's talk about the first one. And these are both quite recent. This is a new talk, so I'm excited to tell you about both of these. Okay, the first work is actually was published in NeurIPS last year. It's called Real-Time Recurrent Learning Using Trace Units in Reinforcement Learning. This was led by my PhD student, Estra. She is great. So the key contributions for this work were we introduced a simple RNN architecture, really actually just a little recurrent unit that allows for very efficient trace-based updates. And then maybe most important is in this work, we really went and investigated how well does this work for reinforcement learning. So there isn't that much work using recurrent architectures in RL. Okay, so I'm going to step through and actually tell you, develop how we get to this particular recurrent architecture and why we can actually get efficient RTRL updates. This is where I'm going to assume there's some set of you here that don't know that much about recurrent neural networks. And so again, we're going to do let's start from the beginning. Okay, so just generically, this doesn't look very RL right now, but I'm going to keep it at this generic level. In a partially observable setting, we don't actually have state. We only have observation. So I'm going to see observation vector x1, observation vector x2, and so on. Maybe these are images, maybe these are sensory information, sensors, for example, in a big control system, any partially observable setting. And our goal is now to infer some kind of state or to summarize our history into a state. So I'm going to call that an S, even though it's not a true state. So we're not really identifying the true state here, but that's our goal is essentially to produce something like an agent state. Okay, so now in order to do this, we're going to learn this state update function. That's what a recurrent neural network is doing. It's taking the previous state that you have estimated, it's taking in the new observation information, learning this function that's going to update that together to give you the next state that you think you're in. Okay, so that's what this diagram is showing. Once you have some summary of the past, so this is incorporating what you thought was your summary before, plus your new information, then you're going to use that to make whatever predictions you'd like to make. So you're still going to produce your y hat. Okay, so these are both going to be some kind of parameterized functions. This could be a deep neural network itself, and this FW is typically going to be simpler. And for us, it's going to be very simple, actually. But anyway, FW could technically be anything in our recurrent network as well. Okay, and so the goal is still the same goal as usual. We're going to minimize some loss. Let's say, for example, you're going to use this squared loss that you'd like to minimize. But let's actually just write this out so we can really feel how painful this process it could be to actually optimize this thing. So if we actually, break out this loss into all its components, we're going to still sum up this loss across all of our samples that we have. We have x1, x2, x3, x4, and so on, and we have all the y1, y2 associated with it. But when we actually write out what we're optimizing, in the first step, we started at some state S0, we saw some observation x1, we made a prediction from that, we produced our new state S1, and we made a prediction about y1, and then we got some loss. On the next step, we're just rolling this forward one more step, but now this is applying that state update function twice. Okay, so we're starting to nest all these FWs, right? So we're starting to roll forward this network. And for each of these, we're really getting a large amount of nesting. Okay, now when we want to take gradients through this, that's exactly what we're going to see. Once we're at some time step I, anytime I want to compute my gradient for how good for my loss here, so I produce some y hat I, this is telling me how good it was. I'm going to say, okay, well, in order to update this, I need to know, okay, how should I have changed SI so I would have done a better job of producing y hat I? Well, that means I need to know, okay, well, how should I have changed W so that when I produced SI from SI minus 1, it would have produced a better SI. But actually, how should I have changed W back here? Because that produced SI minus 1, which helped me produce SI. So you really have to reason all the way back to the very beginning and ask, how should I have changed W so that ultimately through this whole forward pass, I would have produced SI. So this is like a really big, deep feed-forward neural network with a bunch of shared weights. And now we want to go compute gradients. We have a depth I network, and that depth is growing. And so in general, that's going to be a much too computationally intensive process. Instead, in practice, what people are going to do is use truncation. They're going to say, well, no way I'm going to compute all the way back thousands of steps to go compute my gradient. Okay, I'll say in some cases, people use full backprop through time, especially if they don't have things that are too far back in time. But if you have long horizon steps back in time, it's going to be too expensive. So a typical thing is to say, well, once I hit t steps back in time, maybe I can ignore all the gradients before that, and I'm just going to stop at SI minus t and pretend like my gradients are all zero back before that. Okay, so this is one of the most common things to do, but of course this gradient is biased, and it can be pretty hard to select this t to make sure that you're doing an okay job. Okay, so this is all to say the standard, let's just take a big buffer of data, apply gradient descent like we usually do, is going to be a computationally intensive thing to do in the partially observable case. Yeah. Now let's think about what would be our alternative algorithm. There is actually a beautiful trace-based alternative that's called RTRL, real-time recurrent learning. And it, instead of starting at the end and working its way backward mode differentiation, it's going to go forward. So here, it uses this recursive form, and it's actually going to compute the gradients as it rolls forward. And let me explain how it does that, because I think it's pretty cool. So if you think about when you're at this state S2, you're going to make your prediction. So you're going to need to know how should I have changed W? So I would have changed S2 so that then it's going to be better for predicting Y hat. Okay, so in order to do that, you can add, what you're really asking is how should I have changed W here so that it would have produced a different S2? So that's the first part of my gradient. Plus W, how would changing W back in time have changed things? So when you go further back in time, you're asking how would have changing S1 have changed S2? So that's this part. And then using chain rule times how would changing W have changed S1. Okay, so this part is just standard old chain rule stuff. Okay, but the next thing here is that you'll see a recursive form. If I had this gradient of S1 with respect to W, then if I've computed it on this step, now when I want to update and compute the gradient for S2, well, then I just a simple function of this. Once I get the gradient of S2 with respect to W, then for S3, I can again leverage the fact that I've already computed the gradient of S2 for W. So this recursive form lets you compute this as you roll forward. So that's cool. The big issue though here is if you're noticing what the dimensions of these things are. So you don't usually get something for free. Here to actually do these gradients in a forward way, you have to store a lot. So this gradient is n by n squared, where n is the number of hidden nodes. And so that's a large thing that you have to store. And so in general, RTRL is just going to be too expensive for almost any reasonably sized network. You're going to have n cubed storage, again, for that hidden size. And if you've never done this before, you can start taking n's and taking them to the cube and then taking them to the fourth, and you're just going to be shocked at how big those numbers get, like how quickly they get big. I don't know, somehow every time I do it, I surprise myself. And n to the fourth compute per update is just prohibitively expensive, right? Because you have to multiply these large tensors and matrices. Okay. So it's going to be too expensive. That's a shame. That we would love to use this trace space strategy. And this is one of the reasons people don't use RTRL and instead they use truncated backprop. But one thing that has been recognized recently, and it's probably actually been recognized in the past too, is that even though this is expensive for the general class of I have a dense RNN, actually it can be very efficient if we just restrict our RNN to either be a diagonal RNN or a block diagonal RNN. So here, I'm just gonna do a diagonal because that's the easiest one to explain. When I say diagonal, I mean that first weight that we looked at. There's just stuff on the diagonal, nothing on the off diagonal, which corresponds to just saying each element is only impacting the state update for the next, for its corresponding state on the next step. And there's no cross arrows here. So there's only a connection to your next, there's completely independent little states that you have. Okay, so when we do our update for producing S1 from S0, we're just looking at the first element, and all the way down to the nth one is only dependent on the nth element from the past state. Okay, and then they're still both going to take in the whole observation vector. So when you do this, now everything becomes linear. Linear storage, linear computation, everything is beautiful in terms of being able to use RTRL. But this seems crazy. We went from just a regular old RNN to we have all these little independent connections. That seems like we should be giving up way too much. But the natural question here is, do we lose? How much do we lose when we actually go to these diagonals? Okay, and this is where the beautiful result comes in. We actually don't give up too much by making this very restricted our architectural choice. So we gain a lot in terms of RTRL, but if we're careful about it, we can actually still maintain quite a lot of representational capacity. Okay, because it's actually pretty simple to explain, I'm going to do it. So the nice thing is that if you wanted to do a linear recurrence, you can actually reformulate that using a complex value diagonal, and that's where we get the fact that this diagonal is okay. So here, when I say linear recurrence, imagine you wanted to do this. So you're going to update your next state by using your previous state with just a weight, and then we're not going to put any nonlinearity around this. Okay, if you have this kind of recurrent matrix, this W is dense, it's n by n. If you ran RTRL on this, it would be insanely expensive, like I just told you. But we could just rewrite this a little bit if we let's imagine this is the eigenvalue decomposition. You do not have to take the eigenvalue decomposition. This is just a thought exercise about why these are equivalent. If instead we imagine we're learning this S bar, which is just this linearly multiplied thing by S, then this recurrence here is exactly equivalent to that recurrence. Like they're storing the same information, just sort of rotated with this P. Okay, now this lambda here is just a diagonal matrix. You're taking your previous state, multiplying by a diagonal, and then you're incorporating still your observation information. The only thing that's changed is now your diagonal matrix is complex valued and your beta is also complex valued. But people know how to use complex values, so this is a neat thing. So I'll say this is the property that's used behind some somewhat well-known models, like called linear recurrent units is one. Another one is structured state space models. This is one like S4 and Mamba. I'll say actually, interestingly, their goal was about dealing with exploding and vanishing gradients. And actually, there's just these nice things about linear recurrence. So they wanted to use linear recurrent neural networks. But they actually then also exploited this property to make backprop through time more efficient. But those papers were actually not trying to look at making RTRL efficient. So we're going to leverage this exact same property, but we're doing it because we really want to make these trace-based algorithms efficient. And then beautifully, there's all this other work that has shown us that this kind of linear form is actually very powerful for our neural networks. Okay, so what we do is actually very simple. Again, we're building on all this work that has already done so much of this with recurrence. We just made one small representational change in how how we actually represent this diagonal that seems to have been very useful for us in RL and gave us much better results. So I'll tell you what that is. I personally like that. I love when simple things have big impacts. So the architecture we're calling these recurrent trace units. I'll tell you in a moment why we call them that. But if we just contrast them to how what LRUs are doing, the main difference is in how we're actually going to represent these complex numbers. So complex number, I don't know how many of you guys have dealt with complex numbers before, but for some reason they make my head hurt a little. I'm just really used to real value numbers. Complex numbers are just not something I'm good at thinking about. So I'll just tell you there's different ways to represent complex numbers, but there's always this like A plus IB thing. You can, when you actually want to start representing that within a network, you want to do, there's different choices are going to have big impact in terms of actually how easy it is to optimize. So LRUs use this representational form for a complex number, R times exponential I theta. And so you have to learn now an R and a theta. Each complex number is technically like having two real valued numbers here in this two-dimensional space. And then this part is just a dot product I'm writing. Okay, so this is what LRUs for that one unit. This is the actual weight that they're learning. Again, not composed of R and theta. Only thing we did is instead use the cosine representation for complex value numbers, but now it made it really easy to separate out these into two real valued states. So we don't actually have any complex numbers in our RTUs. We just have little block diagonals where there's always pairs of states inside our recurrent trace unit. Okay, so those two, and they're coupled with each other. So if you'll notice what this update looks like, we still have to learn an R and a theta. So our two states still have exactly an R and a theta. But the way you produce the next state is you have to use, R cos theta times the first component of the last state, and then minus R sine theta of the second component of the last state, and then this part's the same. And then this one is just a slightly different formula. Okay, so that's how we're going to represent our complex number. Again, in theory, perfectly equivalent to what the LRU is doing. But now the nice thing is that we don't actually have any complex numbers inside this. We just have this explicit formula that we use. And there's surprisingly a couple of useful ramifications for this. Okay, so we're not going to use any complex numbers. We're just going to use real values. One thing that's really useful is that in an LRU or some of these other ones that look a lot like LRUs, after having a complex number, you produce a complex valued state, and now you have to convert that into a real value if you actually want to go predict real values, which is what we all want to do. So then they have to add this projection and a real value truncation step thing. And this adds a bunch of extra parameters, and it is kind of an under constrained problem. So we don't have to add any projection on the end there. Removing this projection also makes it really easy for us to add recurrence inside the network, which I know the whole point of linear recurrent units was because linearity is what they were after, but actually we were after efficiency. So for us, we found that adding a little bit of nonlinearity in that recurrence can actually improve performance. And so one of the reasons we call these recurrent trace units, because they're really, the point isn't necessarily to be linear. Okay, and then otherwise, just the standard old, we tried this representation, we moved it, we improved it over time, and we just find it performs better, particularly with RTRL, which is what we want to use it for. So, all these previous linear recurrent approaches used backprop through time. They have it working really well in that scenario. And we found this representation just works better with our RTRL update. Okay. Oh, yeah, sure. Go ahead.
Sorry, I had a question because you said you like questions.
I do.
So like the nonlinearity, basically the whole point of like why you get away with diagonal is because of the eigen decomposition that doesn't work once you add nonlinearity. Do you have a sense of what you lose in terms of expressivity by having nonlinear diagonal? Because you can't represent the class of nonlinear recurrent networks. In the linear case you could, but here you can't.
Totally great question. Yeah, we do in some sense in this paper, actually, we worked really hard. We thought, okay, well, maybe this property isn't only true for linear. Wouldn't it be beautiful if we could figure out which F is it also true for? Sorry, which activations, let's say, is it also true for? In the end, we kind of proved a negative result where we have an if and only if relationship around the types of F that have this transpose property where you can like swap, if the P can come in and out of it. And it's this really weird class of functions F that no one would ever use. So I would argue that largely this is only true for linear functions. And we're definitely just losing this property from there. One of the next things we want to do is actually see, can we at least empirically start to understand what happens when we do this F? Yeah, totally. Yeah.
So it's kind of like a dual of what Rizwan was asking. There's a cottagecore industry of like online approximation, the backprop through time, and RTRL, like RFLO, RO, a lot of acronyms that half of them I forgot. So like all of those kind of trained expressivity with like compute or memory. So you take the 3D tensor and you break it up in sub-elements and you try to build recurrence for those instead. But they keep the model as maximally flexible. Here you're sort of like I'm going to change the dynamic systems class, but do exact RTRL in that. Do you have a sense of like how does this trade-off play empirically or?
Yeah, great question. Just to repeat the question. Most people have done the very sensible thing of saying, you have an RNN you want to train, let me train it for you better by approximating the gradients in some smart way with like low rank approximations. So it's efficient, but you're training the thing that you actually want to do. We're saying we don't know how to train those things. We're going to restrict ourselves to this class and do it more exactly. Now, how much are we actually giving up between those two? Yeah, great question. I don't actually have an answer to that question. There is some work on the expressivity of these kinds of linear recurrent networks, and there's just surprising like expressivity results, but what they can express. All I can say is empirically for ourselves, for many of the RL problems that we're looking at, which look a lot more like summarizing relatively recent-ish histories of things like trajectories and smooth kinds of behavior, this level of expressivity seems to be sufficient. But I deeply want to answer this question. So if anyone in this room has answers to this question, it would be great. Okay, I'll continue. Okay, yeah, so part of this was motivated by performance. I'm just going to show you guys a couple of results, and then I'll move on to the second part, although I intentionally spend a little bit more time on this first part, and I'll do a little less on the second. Okay, let me tell you what this plot is showing. So we ran many different benchmark environments. We particularly used the Majoko POMDP benchmark, which is take Majoko and then add some partial observability to it. We layered this on top of PPO. That like we used the PPO algorithm and then just swapped in different architectural choices. So they all use the same PPO. Okay, now let's tell me what this plot is showing you. So on the x-axis is how many steps of interaction there are with the environment. Y-axis is online performance. Like, we're actually looking at how well does the agent do as it's interacting with the world. And this is averaged over 30 runs with 95% confidence intervals. So the key algorithms to notice here are nonlinear RTU and linear RTU. Okay, just RTU is the linear version where we're using our cosine representation. Nonlinear is we just add a nonlinear activation inside that recurrence. Those two are essentially the same right now, so that's not really motivating what I said earlier, that empirically we find this helps. Hold that thought for now. And then otherwise there's the LRU here. GRU is just a standard gate of recurrent units. And then online LRU is taking the LRU, but then doing the RTRL form for that LRU. Okay, so a couple of interesting things is that already there's a gap between LRU and online LRU. So the RTRL form for LRU is helpful in this somewhat resource constrained setting. So what we did for these experiments is we didn't let LRU have any large truncation level that it wanted. We picked some truncation level that had a fair amount of compute. And then so this is how you see this gap. And then in the paper, we do show performance for different truncation levels. So you can see when there starts to be a corresponding similar performance. So anyway, there's already a gap here between just using LRU and online LRU, and then a further gap from this difference in representation. And then the GRU seems fine. Again, this generally, we found this theme mostly throughout all the rest of the benchmark. So I just showed you this first plot. It's kind of overwhelming to see all these plots at once. So I just described for you one plot first. But in general, you're seeing kind of similar behavior across many of these environments. If there's anything else interesting to point out, maybe not. You can also go look at the paper for a few other environments, like we did some experiments in PopGym. We also did some simpler experiments in the prediction setting. We use these kind of trace conditioning experiments with stimuli and stuff from an older literature. Okay, so that's so I just want to give you a flavor of what the results look like. We were excited that we could actually get such significant benefits from, again, very minor changes. Yes.
Sorry, in the linear case, is it embedded in the transformer block for the MLP, or is it just the linear? Like, sorry, how does it look? Because for the SSM, the MLP block above is crucial.
Oh, great question. Yeah, okay. So these other works with like LRU and so on have particular architectures. They stack a bunch of these and stuff. Okay, I'm gonna be fair here and say that we did not do any of that actually. We really didn't want to ask if you took an LRU and used exactly the kinds of architectures they use, what would happen? We wanted to know if you just had a simpler RNN for these environments where you could already perform with a simple RNN. How did these different representations change things? So we just had we would have had an MLP. We definitely had an MLP after the LRU, like after the recurrence, but we didn't have multiple LRU layers stacked. That is a good thing to do next, though, is to actually do the multi-layer recurrence setting.
Okay, but you had at least one MLP.
Yeah, absolutely. Yeah.
Hello, I have a doubt. So here it looks like you're considering only diagonalizable linear systems, right? So, but from classical linear system theory, there is a drawback from using only eigen-decomposable functions. Sorry, the state transition matrices. That if you have a non-trivial Jordan block and your data was generated from this trajectory,
Okay.
then there is no finite dimensional representation for approximating with a linear system, right? How do you deal with that scenario?
Okay, you're gonna know more about this than I am, but I would argue that, I guess the point about the diagonalization is just, here's the case where these two things are equivalent. So if you do have a linear system that is diagonal, where the weights are diagonalizable, then you're gonna be able to have this equivalence property. You may as well have just had a complex value diagonal. It doesn't say anything about linear recurrence is sufficient to model whatever RNN, like whatever thing you're trying to model. Does that answer your question? Okay, come talk to me about it more after. Okay, a couple other things I'm not going to actually show you results for, but these results are in the paper. We did try to test little things. So whenever you have a surprising result like this, like how could it be that just this cosine thing had such a big impact and we just had two revalued things? You really have to, we tried really hard to break it because we don't want to mislead ourselves. So we did things like, what if we didn't couple them and we just made them like two real valued block diagonals and things like that. So we found this actually keeping them as complex numbers really did matter a lot. So this coupled update mattered a lot. Also pointed this nice paper, not from my group, it's actually from Nadav Cohen's group, showing how important it is to use complex parameterizations and how they scale a lot better than real valued ones. Another interesting thing too was with LRUs, of course, we could get them to get to the same level of performance when they use truncated backwrap through time by just increasing that truncation length. So at some point we got to the same level of performance, but we did interestingly find even then the step size sensitivity seemed to increase as we increased this truncation length. So there's even there a little bit of benefit from using RTRL. And then, though maybe not obvious up front, there's actually two ways that using these kinds of RTRL updates can be useful. One, of course, is for computation, which is what I motivated, but there's also utility for bias. So in all our prediction experiments, which I did not show you, these are things like in trace conditioning, there are significant compute reductions for using an RTRL approach rather than truncated backwrap through time, because everything scales with T in that case. Larger is T, the more your compute goes up. In PPO, the way that most RL algorithms are implemented with recurrence, there's not really a difference in compute because the way you're blocking things up, people don't use overlapping, they don't overlap the batches when they compute these updates. This is a little too complicated to explain here, but there's no compute difference in the batch way because of the way things are computed in PPO. But because of that, PPO, then when you come to the beginning of a batch, it's like your T is shrinking and you actually are incurring even more bias. So again, RTUs here are actually going to avoid that bias. So you don't get computational wins in that case, but you do avoid this bias. Okay, to give myself just, let's say 10 minutes to do the second part, it should be sufficient. That's all I'm going to tell you about. Traces can be very useful for us in the partially observable setting. And there doesn't seem to be that much loss for moving to this simpler architecture. Okay, let's talk about the other way that we're going to use traces. You're going to see the same smiling face here, and this is also with my PhD student, Brett. So this is recent work just published at RLC about using gradient methods for deep RL with eligibility traces. And so here our key contributions are taking some of this work on projected Bellman errors and extending it to use lambda returns so we can actually derive sound gradient-based methods, and then providing two concrete instances, algorithms of these methods. So let me actually this is pretty technical, so the only way I'm going to be able to explain it to you is to get to these next slides. Okay, one thing I've been doing for a long time is working on gradient-based methods. It's like the number one thing that I work on. So my lab has really been working on this for a long time. We've really been chipping away at this problem, and I feel like we have finally cracked this nut. I'm happy with the answer that we have to this question. And so let me just tell you what the problem is. The problem is that for most of RL, TD is temporal difference learning underlies most of RL, Q learning updates, TD updates, STARS updates, actually PPO stack, all these algorithms are built on top of TD. But TD is usually called the semi-gradient method, which is a nice way to say it is not a gradient method. Yeah. And so it can diverge under nonlinear function approximation. And we sort of know that we have this thing that underlies our algorithms that's not quite sound. So that's the thing that we've been working on a bunch in my group. And somewhat recently kind of brought all this work together. We introduced the generalized projected Bellman error. That makes it a lot easier now to actually derive these kinds of sound algorithms for the deep RL setting, which means when you have neural networks. So there was a lot of work in the linear case. It was hard to extend it. We have finally made it easy to actually drive these algorithms. And we're finding that they perform a lot better as well. Because of this generalized objective, we also made it really easy to do other things we love to do in optimization, like add robust losses. So we went and got some versions of these algorithms with robust losses, again, saw some improvements. And the other nice thing too is that these algorithms seem to perform well without target networks, which for us is a boon, again, in the continual learning setting. Remember, we're learning hundreds of things. We don't want to have to store secondary networks. We don't want to have to figure out when we're going to update those and have these extra hyperparameters. Okay, so we would like to take these gradient methods and extend them to the case where we haven't extended them to yet, which is all this work. We had done it with the case where lambda was 0, which is the same as we did this, saying this, we did this for one-step setting, but we really like to have more sample efficient methods, and lambda returns are critical for that. So let me tell you now what a lambda return is, for any here who don't know what that is. Okay, so in the very beginning of this talk, which, you know, I'm assuming you perfectly remember all the math notation I gave you up front. So in the beginning, I mentioned we could bootstrap off of our own value estimates. That's a very common little one-step update that we do. This is sometimes called the one-step return. It is also the case where we call this lambda 0. So there, as our targets, we're going to say my target is my immediate reward plus gamma times my guess of what I'm going to see into the future. On the other extreme is saying, I'm actually, when I take this action, I'm going to wait to see all my rewards into the future. I'm actually going to compute my return. I'm going to get a sample of my return. And in order to get that sample, I'm just going to have to wait t steps to see it. Okay. In fact, I'm just going to pull up this little picture. So like, I'm here on state ST. I need to look into the future to see what is going to be the outcome of taking my action. And so in order to do that, I don't actually get to look into the future. I'm going to have to wait until I see it and then go do my update. Okay, so this Monte Carlo return is honestly what people largely use to like train large language models now. So there's a lot of utility to using these kinds of long range returns that let you know what was the outcome of my action now. You really get to see t steps into the future. That can be very helpful for assigning credit to your action. So that's what I mean about credit assignment. These longer Monte Carlo returns are going to be good for credit assignment. But as with most things, the two extremes of things are rarely the best. And what we'd like to do is maybe something in the middle. So this lambda return is going to say, well, this is going to be a high variance quantity. What I'd rather do actually is say, I have my immediate reward, and now when I'm going to bootstrap, I'm going to balance between two estimators. I'm going to trust a little bit my value function. It's going to tell me something in a more low variance way what's coming. So 1 minus lambda times that, plus lambda times the stuff I'm going to see into the future. Okay, so the lambda return is kind of like the Monte Carlo return, but it's sort of letting you balance and reduce the variance a little bit. So we'd like to extend from this one-step kind of thing to this setting. Okay, and this is where traces are going to come in. We can always do this thing where we actually wait. So even for lambda returns, just like Monte Carlo returns, we would have to wait and see all these rewards and go and compute this, average thing into the future, which is what a lot of methods do, like PPO and so on does this forward view. But there's actually this beautiful result that says we can take all those updates that we would do if we were to wait, but actually we can reorder those updates and we can actually send back information. So we can say, once I reach this state, I can tell all the states behind me, hey, here's the update you would have done, and you can just apply that update now. So the updates are done in a different order, but they are the same set of updates. So the back review is going to use traces of information, and it's going to be able to send things back instead of doing it in the forward way. Okay, so that's what we did. We took our projected Bellman error, we reformed it as a lambda return, and then we derived some forward view algorithms and some back review algorithms. Relatively standard stuff, but I want to show you what the actual algorithms look like. I'm not going to be able to go into those derivations. That would take too long, but it's kind of nice maybe to see a little bit about how it can look a little different with the gradient-based view. I hope this part here doesn't scare you away from using these gradient-based methods. It's honestly not that complicated, but I think it's maybe a little informative to see how these algorithms look. So in this is a regular lambda using eligibility traces for Q learning. So if you were to incorporate this into Q learning, your trace might look something like this. So you're gonna be storing all these gradients that you saw along the way. And then the delta T is this TD error, is that difference between your one-step, what you think your one-step return is and what your current estimate is. But you're actually sending that TD error back to all the gradient updates along the way. So this is sort of like that calling back procedure. That's the intuition of what's going on here. So this is Q lambda. And then over here, what you have to do for gradient methods to actually make this a sound update, all the gradient methods learn a secondary function H that is trying to estimate a part of the objective function, and then it uses that to let us update. So this H, now we have a second set of parameters, theta. We're going to have traces for both of those parameters. Interestingly, I did not expect this to happen, but when we actually drive this algorithm, we also have a trace of the estimates of that part of that objective function, and then our update looks a little different. So just maybe an interesting thing to point out is the update for W, which is our main value function estimate. It's the same part. This part is still like the TD part, but you have what's called corrections or gradient corrections here that you have to kind of adjust your update to make it a sound update. That's actually where the name QC and QRC comes from. QC means Q learning with gradient corrections. The R stands for regularized because this regularizer actually really matters. Not going to tell you about it now. Okay, so that's what the two algorithms look like in the last few minutes here that I have. Let me just show you some of the results we have with this. So what we're going to compare here to is really we're asking how important was it that we added these modified to be these gradient-based algorithms. Like I said, we already have eligibility trace methods, but they're built on TD. So we want to have the gradient versions. Okay, so to test this, we looked at a benchmark called Minotaur, which is taking something like Atari and then trying to make a simplified version of it. So mini Atari, so that's a little bit easier to run experiments. Okay, so again, same thing as before. X-axis is all our steps of interaction. We're looking at how did you do online? What was your online performance? Averaged over 30 runs. Okay, and there's 3 algorithms listed here. Q lambda was that thing I just showed you. So no one in RL would have been surprised by that straight line at the bottom because no one uses Q lambda for a reason. It's not an easy algorithm to, it just doesn't really work for these kinds of deep learning settings. Stream Q is a recent algorithm that actually got eligibility traces working. It's a nice result, but still built largely on TD-based methods. And then QRC is just doing better. That's what this result says. Okay, and then just showing you this, just like before, I'll just show you how this generally seems to be a theme across these this benchmark suite that we have, that the gradient-based method is actually helping out. Okay, I'll also just point out that we also did this with PPO. So we took PPO. I'm not going to tell you how PPO works, but underneath PPO also estimates value functions, also uses a TD update for estimating value functions. We swapped out that update and we swapped in our gradient-based update for the value function. So we're calling that gradient PPO. It's some interesting thing here that takes us a little longer to learn, maybe because it takes us a little longer to get these H correct for that value function, but seem to get to better performance. And this was in Majoko, by the way, not POMDP Majoko, just regular Majoko. And then in other cases, we see somewhat similar, slightly slower learning, and then just otherwise comparable performance. These two, we see slightly better performance. Okay, I think I should wrap it up. So that's all I wanted to tell you about. Traces for partial observability, RTRL, training our networks for the partial observable case, and then traces for doing faster credit assignments, so sending back as much information as you can, try to make each update really count. Just want to tie it back to what we were talking about because I'm motivated, then we did a deep dive. We've all forgotten what we were talking about, so let's pop back up. All the experiments I showed you were in the episodic RL setting. They were all stationary. None of that feels too much like continual learning. So I just want to remind you that continual RL to me means that we need to learn subtasks continually. So the main agent still is in its big complex world. It's probably in a continuing problem. But still each subtask it's going to learn little options and value functions is probably something like a simpler episodic problem. So these algorithms are useful for that part. And for this subtask learning setting where you're learning many things in parallel from one stream of experience, I think trace-based methods can approximate sort of the sample efficiency that we get from doing a bunch of munching on a buffer, but in a much more computationally efficient way. And this last point here, though we didn't really discuss it, I do also think that these methods, using these kinds of trace-based methods, should be more effective under non-stationarity. It's just sort of sweeping back the most recent things that are happening in a natural way, rather than having to decide in your buffer what's new and what's old. Okay, and so this last slide, key algorithmic takeaways. Trace-based algorithms can perform well with careful algorithmic choices. They've kind of been ignored for a while. Buffer-based things became the norm. I'm still a huge fan also of buffer replay plus buffer-based approaches. Like for some problems, that is just the right thing to do. But we've sort of been neglecting this other class of methods that have these nice sample efficiency plus computational efficiency properties. And the time is to revisit them. They really can work in this deep RL setting if we're careful with how we do it. 2 ways we can be careful about it. One is to be careful with the RNNs that we actually pick, and we can get good and efficient learning. One is recurrent trace units. I encourage you to go try it out. Email Esther if it's not working. She'll love to talk to you about it. And that if we also use gradient-based methods for eligibility traces, we also seem to get a better performance, more stable, consistent performance. Okay, that's everything, and let's chat.
Any questions?
There's one behind you.
Hi. So if I understand how it works, like if you stack RTUs, then you don't get the efficiency anymore because you get sort of the cubic cost in the MLPs for which you need to backprop. Is that right? And is that kind of like a fundamental limitation in some sense? Like, do we know that is enough to have one single recurrence layer and then everything else can be feed forward?
Yeah, great question. The point was very astute. The point was that if you start to have multiple RTU layers, and they're now going to all start getting coupled, and you're not going to have this nice efficiency anymore. Absolutely right. And ESPO's working on it, but yet it does seem like that's just fundamentally a problem. And then is the implication therefore that we should just have one single layer? I mean, the implication could be that we do have multiple layers, but we do things like try to approximate. Now we start getting back to approximations, or we don't pass gradients back. There is also this work from my other previous student, Kurum, that looked at, it was called columnar networks. It looked at having some depth, but still keeping these blocks. Like you could have some depth and recurrence, but the blocks themselves would be independent. And there, I believe you can still get some efficiency. But yeah, I don't know yet. I actually am still out on the question of, do we need multiple layers? There does seem to be some of these papers that are keep the recurrence simple and then add a lot of capacity on the neural network side. But that, so you can hear me not being sure, because I would love if someone could tell me, what do our recurrent neural networks providing us? Like, I just don't understand their capacity yet.
Hi. So one thing that was interesting about the way you parameterized the complex numbers in the part 2 of your talk, I guess, is that it like is a nice sort of polar coordinates representation where you've disentangled like norm from direction or length from direction,
Right.
which has been found to be super helpful in like a really broad range of like machine learning problems. And I was wondering if you had a sense of like how much of the benefits you saw came from like this parameterization versus like the interpretation of this as being a complex number.
Okay, that's an interesting point. Interpretation as a complex. I mean, it could be a little bit of both. I mean, we do think that that separation could have made maybe like an nicer lost landscape or something like that. But I think the complex, it doesn't necessarily mean that that was the only benefit. It's hard to say, because we also did this thing where we did 2 real valued states that had no constraints on them. And again, that performed much worse. And I think maybe what you're saying is maybe it performed worse, not because it wasn't a complex number, but because it didn't have some kind of these nice properties. I guess I don't know. I would love to maybe come tell me more experiments you're thinking of, then maybe we can try to get rid of that confounder.
Any other questions? Okay, well, if not, let's thank Martha once again.